Hi, my name is Lingpeng, and indeed I'm come from CMU. Thanks everyone for being here. Today I'm going to talk about our work of building a dependency parser for tweets. This is a joint work with Nathan, who is now a postdoc at the University of Edinburgh, Swabha, Archna, Chris, and I'm my advisor, Noah Smith. We tweet every day. It's also a hot topic in natural language processing. On one hand, we use tweets to make predictions. For example, we do sentiment analysis. On the other hand, the informal nature of the language on tweets is a big challenge for the traditional NLP pipeline. Unlike the standard newswire text, tweets often contain a lot of non-standard spellings and non-standard use of language. We can see this in these examples given by Jacob Eisenstein. So in the first tweet, there are a lot non-standard spellings, and in the second tweet, the use of the punctuations just look kind of random. Important steps have been taken in building NLP tools for social media. We now have a tokenizer for tweets. There is the POS tagger developed by Kevin Gamble et al., which use a specific design tag set for tweets. And we also have an NER system from Alan Ritter. So Michelle Obama is a name entity here. The English tree bank, which lies somewhere between the newswire text and the social media messages, has been created. That was sufficient to support a shared task on parsing the web. In order to give you a direct intuition of the huge difference between the standard newswire text and the tweets, let's take a look at an example sentence taken from the pantry bag. Unlike the tweets we just saw, the language here is so much different. Does anyone, willing to believe that this can be a tweet? Probably no one. So if you tell me there is one person ever tweet like this, with so formal capitalizations, so accurate vocabulary, and above all, so perfect grammar to handle such a long sentence like this, I will guess the answer can be only him, the creator of the tree bag. Okay, so beyond the impression we have, let's see some numbers. So Tim Baldwin et al. Give a great quantitative analysis of how different Twitter data is. Here in the table, larger the number means larger the difference. We can see from the Twitter data, that the Twitter data is the ones most different from the Wikipedia and the PNC corpus, which can be seen as a representative of the formal English, like the pantry bag. Given so much difference, it is no wonder that if you want to mainly rely on the pantry bank resource and train a parser for tweets, that will be difficult. Mark Duritz and Jennifer Foster all found this is very hard. A more important question here, I believe, is should we really fit the Twitter data to the annotation guideline, which was designed for the pantry bank? I guess the answer is probably no. What we think we should do here is we need to fit the parsing task to the Twitter data. This paper is our attempt. So in the remaining of the talk, I will talk about how we build a new dependency parser for English tweets. We just do things every reasonable people would do when building a new parser. I will go through these points one by one, and I will highlight the different things we did. First, we need to have annotation guidelines. Given the Twitter parsing task, how we change the annotation guideline so that it really fits the data. It really fits the task. And then we have to have annotated corpus for the use of training and test. But if you have a shoestring budget like us, we are so poor that basically we have no money other than ordering some pizza. So what can we do here? Third, given given that we have a new annotation guideline, we will need to adapt the parser to output consistently with it. And last but not least, we would like to know if there are features other than the traditional ones are useful specifically for the Twitter parsing. I will start with different things we do in the annotation convention. The first impression we have as an NLP researcher when we see the Twitter data is it's very non-standard. By non-standard, we probably want to say that it contains a lot of syntactically unrelated tokens, which are not usually seen in the pantry bank corpus, like the URLs, the retweet symbols, and the irregular use of punctuations, and so on. We argue that not all the tokens are syntax. Therefore, the first thing we did here is, instead of having an ugly tree with all the syntactically unrelated tokens included, we remove those tokens from the dependency tree in the first place, so that we get a dependency tree not over all the tokens of the sentence, but over some selected tokens of the tweets. But keep in mind, we do want to include those syntactically related tokens inside the parse tree, even if they are hashtags or something like that. In reality, this is treated as a pre-processing step. We train a first-order sequence model using perceptual, and we find it's a pretty easy task for the machine. The accuracy is about 97%. Another thing we want to have here is the multi-word expression. There has been increasing attention on the problem of multi-word expression. Here we argue that from the annotator's perspective, these multi-word expressions should be a single node inside the dependency tree. So we give the annotator the freedom to group those words as explicit multi-word expressions. Those including proper nouns, connectives, and so on. We think that to annotate the internal structure of multi-word expression can be confusing to the annotators and can be a waste of annotators' time, since the internal structure is not always very crucial in downstream applications. The last thing I want to highlight here is multiple roots. In the pantry bank, single root is assumed. We parse one sentence at one time. However, in tweets, we often contain multiple sentences or fragments, which we call utterance here, inside one tweet. So the solution we propose here is we allow multiple attachments to the word symbol, like the example here. So this is not very painful thing for a parser, and we should do that. Okay, let's recapture what we changed in the annotation guideline. So first, we selected syntactically related tokens. And second, we allow the annotators to group those multi-words, expressions. And later, we have multiple roots over all the multiple utterances. And finally, we have a dependency tree like this. Okay, so the second thing I'm going to talk about is our annotated corpus. Like I said before, we have only a pizza. What can we do? So unlike the pantry bank annotation, which take years and involve thousands of person-hours work by linguists, the tweet bank we have is mostly built in a day by 24 annotators with only a few training in the annotation schema. We believe that even the annotation is not perfect here. We can hopefully still train a useful parser based on that thing, as long as most people did the right thing. So here is a photo of us annotating the data. We all pretend we are working hard, at least in front of the camera. And here is not many people want to sit with their advisor, especially when annotating the data. And we also have an amazing team from UT Austin helping us online. So to achieve a faster annotation speed, we employ the graph fragment language. It is designed to facilitate the keyboard entrance of parsers. For example, if we have a Twitter like this, we can annotate the parse with only a few edits. We also have a fancy web-based annotation interface, which can assign the tweets to the annotators and can give them instant feedbacks. Okay, so with all this, at the end of the day, we have the tweet bank, which contains more than 900 tweets with manual dependency parsers. The tweet we labeled are drawn from the POS tagged Twitter coupons, so that we have the gold standard POS tags. We also measure the inter-annotator agreement, and that's above 90. So tweet bank is then split into train and test set. The tweets in the test set are from the most experienced of our annotators. Given the limited data, we believe using the highest quality data for measuring the performance and lower quality data for training is a sensibly realistic choice. Now we have the annotated coupons. In the next few slides, I'm going to show that how we adapt the parsing algorithm to output consistently with our annotation guideline. In particular, remember we do the token selection when annotating the data. How do we tell this to the parser that we did this? The most straightforward way to do this is we just use the out-of-box parser. But we need to remove all the unselected tokens from the sentence first, like this. Because traditionally, the out-of-box dependency parser assumes every token inside the dependency tree. But it is obvious that this is losing information. For example, intuitively, we know that the majority of the dependency arcs, they do not go across the punctuation. However, since we remove all these tokens from the sentence in the first place, we have no access to this information anymore. So ideally, what we want to have is we want these unselected tokens to be visible to the feature function, but at the same time excluded from the parse tree. To do this, we adapt Turbo Parser. Turbo Parser is a graph-based dependency parser which solving the parsing problem by finding the maximum spanning tree Y over the given input sentence X. A key attraction of Turbo Parser is that many overlapping parts can be handled, making use of separate combinatorial algorithms for efficient handling subsets of constraints. For example, the constraints that forces the Z variables, which representing the existence of an arc, to be a valid tree, can be exploited within the framework by making calls to the classical COE algorithm. To make unselected tokens visible to the feature function, but excluded from the parsing tree, we did not change the feature function. And neither did we remove those unselected tokens from the inputs. What we do is we adapt the decoding algorithm to exclude unselected tokens from the tree. Concretely, in the AD-cube decoding framework, we constrain the binary variable representing the existence of an arc, Zij, to be 0, wherever Xi and Xj or Xj is unselected in the parse tree. For the first order model, this is all what we need. And for the second order factorization, which considers sibling and grandparents, since Turbo Parser decodes them using grand-sibling head automata, we also need to remove head automata involving unselected tokens as parent or grandparent, and the transitions that consider unselected tokens has to be eliminated. We examine the effects of parser adaptation by doing a single ablation of it from our final system, which contains all the changes we made to the parser, including some features we are going to discuss in the next few slides. So we get almost 2 points on our test set by employing this adaptation. As the last step of building a parser, let's look at if there are features which are useful to the Twitter parsing task. Although we choose to develop a parser from scratch, it is hard to ignore the pantry bag, which is such a large amount of high-quality syntactical data. But Besides merging our training set and the tree bank into one, which probably is not a very good idea given that it's so different and our training set are so small comparing to the pantry bank. Our solution is a stacking-inspired incorporation of pantry bank information into our model. So concretely, we independently train a first-order model on the pantry bank. Then we parse the tweets using this model. Like in this figure, we can extract the scores of every candidate arc pretty easily. And then, as a second step, when we parse the tweets using our model trained on our training data, besides the traditional features we considered, such as word form and POS tags, we define a new feature on every candidate arc whose value is the score of the same arc under the pantry bank model from the previous step. So this lets a pantry bank model literally weigh in on the parse for the tweets and lets the learning algorithm to determine how much consideration it deserves. As a result, we get 0.7 points in our final system by using these pantry bank features. The next thing we try is Brown clustering, which found to be very useful in dependency parsing and Twitter POS tagging. We implement Brown clustering features following Terry Ku's paper. The cluster we use is from a very large Twitter corpus. The result is a little bit unexpected in this case. The Brown clustering doesn't consistently help in our final results, at least in our test set. The reason is probably because the training set we have is too small. Therefore, it is hard to get a good estimation of the parameters for these features. Okay, so we have go over all the steps of building a parser. Let's look at some final experimental results. Besides the test set we created, we also test our parser on the test set annotated by Foster et al., converted to our annotation convention. Here is the final result for our main parser, which has all the things we mentioned above included. We achieved 90 point, I hope we achieved 90 point. We achieved 80.9 unlabeled attachment score on our new test set for Twitter parsing. This is on par with state-of-the-art reported results for news tests in Turkish and Arabic. The number here is a little bit lower on Foster's dataset, but we think that the result on our test set is probably more representative for this task, because our samples are randomly drawn from tweets in a day and through a year and a half. Despite its obvious temporal screw, there's no reason to believe this sample is otherwise biased. However, Foster's dataset is drawn from a corpus with predefined topics such as politics, business, sports, and entertainment. In short, topics not unlikely to find in the pantry bank. The out-of-vocabulary rate comparing to the pantry bank training set proves this point. The OOV rate by type of our dataset is around 45, which is pretty high, while the Foster dataset is only around 21. For reference, the out-of-vocabulary rate for the pantry bank standard test set is around 13. Okay, let's look at some other results of the experiments. We see from this table that, not surprisingly, with either gold standard POS tags or gold standard token selection, the performance increases by 1.1, and with both, it increased by 2.3. Another experiment we did here is to directly train a parser on the pantry bank and then test on our test set. The baseline here is an off-the-shelf second-order turbo parser, trained on the pantry bank, converted to our dependency convention as close as possible. We are encouraged to find that on our test set, our overall approach obtains a 7.8 gain with an order of magnitude less annotated data. So to conclude, we built the Tweeble parser, a dependency parser for English tweets that achieves over 80% unlabeled attachment score on a new high-quality test set. We also have the tweet bank, a corpus of more than 900 tweets with manual dependency parsers. Additionally, we have the adaptations to a statistical parsing algorithm and a new approach to exploiting data in a better source domain, which is the pantry bank in this case. And everything is available online, including the code and data sets. Thanks, everyone.
Okay, we've got plenty of time for questions. Okay. I'll let you take it. Sit.
Great talk, thanks. Have you ever tried to do joint token selection and dependency parsing?
Yeah, I think that can be done, but we didn't do that because we think that the token selection accuracy is above 97. So it's probably not much again there. So that's the reason we didn't do the joint model here. Yeah.
Hi, great talk. So I was wondering if you observed the opposite problem in your data set where some tokens were instead missing in the sentences, and if you had any thoughts on modeling that in your parsing model.
Excuse me, but what do you mean by missing the token?
For example, instead of having a sentence like Justin Bieber is a great singer, you had a sentence Justin Bieber, great singer. And in that case, would you have to explicitly model these missing tokens in your parsing algorithm?
I guess my guess is that this kind of sentences, as you mentioned, missing a lot of things. It's a nature of the tweets also. So that I think we must have that in our training set. So we leave the learning task for the parser. So we're training on that parser, and hopefully it can catch the phenomenons like this. Yeah.
Thanks.
Thank you.
Great talk, thanks. What's the baseline accuracy for token selection? Like if you just said keep everything.
Oh, that's a good question. I think we can see from the data set that the selected tokens is about the half. So if you select all the tokens, it should be like 50. And maybe if you do a simple, filtering on the POS tags, like you filtering those at labels and hashtags, something like that, the punctuations, the accuracy is probably higher. If I remember correctly, it's like 90% something. But we do a sequence model, which is no harmful, but we achieve better score here.
All right, thanks.
Thank you.
Yeah, thanks for the talk. This is a very useful resource. I think that given the size of this, since this opens the possibility of doing lots of important experiments, we should try to, it's more, this is more a remark. I think we should try to do more cross-validation evaluation, such that we can use the full tree bank as tests and maybe not overfit as a community. It seems that the test is small, and so we might overfit to the test itself, so it's pretty easy to then, given the data, to run cross-validation experiments. Just a remark.
Yeah, I agree that it's true. And another point is maybe if we have more annotated data, we can hopefully train a better model, because more training data seems to mean better accuracy in a sense. But I think our setting is that, we have no money to label so much things. I think, yeah, here is the thing is we want to assume that we have only a little bit annotated data. And hopefully that this field data can help us to go a little bit further. Yeah, that's the reason why the adaptations and the PO and the pantry bank features are important, I think. Yeah, thank you.
Very nice talk. Thanks a lot.
Thank you.
This brings me to the next question. Did you try to do any semi-supervised learning already?
Oh, I didn't do that. I don't know if Noah told someone to do it. Yeah, but I think semi-supervised learning in this kind of low resource domains can be a very good idea. And we can have multiple ways to do that, like the brown clustering things, and we also, can do some, spectral things if you want. And I think that's really promising.
What about hashtags? So how do you go about modeling the dependencies of these kind of things, which can be, they can function as punctuation and they can sometimes function as actual nouns and verbs and so on in the sentence?
So that depends on its function inside the sentence. So like if you have a hashtag which is used as a noun, that should be a noun. Remove the hashtag and see that is a noun. So that's its function inside the sentence, and we did that. So it's not because they are hashtags or something we treat that specifically. We have that in our sentence.
And your feature representation is enough to sort of unify the hashed version of a word and the non-hashed version, and so
I hope so. Yeah.
Okay.
Thank you.
Any further questions? Okay, well in that case, let's thank the speaker.